Welcome to Ultra-Concurrent Laboratory on Non-Inverting Operational Amplifier. It has two different configurations, standard configurations and high-gain configuration. This laboratory in total has 216 different non-inverting operational amplifier combinations. The standard configuration is used to observe the relatively low and medium voltage gain of the amplifier. The schematic view shows the variations in 4 circuit parameters and 1 signal parameter. In the schematic of standard configuration, it is possible to select one of the 3 possible values of resistor Ra. Similarly, it's possible to select one of the 3 resistance values of feedback resistor Rf. This laboratory also has the feature of varying the input signal voltage and frequency. The input frequency can be one of the 3 values, and voltage can also be one of the 3 possible values. And there is an option of selecting op-amp with lower and higher performance parameters. The circuit view shows the real-time implementation of non-inverting operational amplifier on the breadboard. The LEDs indicate which combination is being in action at the given time. Oscilloscope view shows the time response of the non-inverting operational amplifier. Oscilloscope has 2 waveforms where yellow corresponds to input and the blue corresponds to output waveform. The Bode diagram shows the frequency response of non-inverting op-amp. Let's start the analysis with Ra of 1 kΩ, Rf of 10 kΩ, voltage of 100 mV and frequency of 100 Hz with mu A741 op-amp, which is having relatively lower performance parameters. With the input sine wave frequency as 100 Hz, observe the peak-to-peak amplitude of input 208 mV and output 2.2 V respectively, thus confirming gain of nearly 11 in magnitude. The output signal is in phase with that of input. The Bode plot of the circuit also shows a DC gain of 20.98 dB at a low frequency 202.06 Hz, and the corresponding phase is almost 0 degree. The 3 dB bandwidth is found to be 42.6 kHz. If the gain of the amplifier is changed to 2 V per volt by choosing the resistance values of Ra and Rf as 10 kΩ, the oscilloscope view shows a gain of almost 2, and the Bode plot readings are DC gain of 5.966 dB at 200 Hz and 3 dB bandwidth increased to 355 kHz. This demonstrates, as the gain of amplifier decreases, the bandwidth increases. The above process is carried out for another op-amp OP37 with better performance parameters. In the first case, with Ra equal to 1 kΩ and Rf 10 kΩ, the voltage is gained 0.805 dB and 3 dB bandwidth is 8.132 MHz. This shows that the op-amp OP37 with larger open-loop gain has better bandwidth compared to that of UA741. Like this, the analysis can be done for other combinations of resistors, signal amplitude and frequency. In high-gain configurations, it is possible to analyze the performance of the amplifiers up to a gain of 101 V per volt. Let's start the analysis with Ra of 1 kΩ, Rf of 100 kΩ, voltage of 5 mV and frequency of 100 Hz with UA741 op-amp. With the input sine wave frequency as 100 Hz, observe the peak-to-peak amplitude of input and output are 11 mV and 1.10 V respectively, which demonstrate a voltage gain of close to 101. In the Bode plot, the DC gain is 40.11 dB and phase is almost minus 0.172 degree. The 3 dB bandwidth is found to be as low as 9.3 kHz. A similar analysis for OP37 shows a DC gain of 40.08 dB and a 3 dB bandwidth of 517.03 kHz. This again confirms that op-amp with better performance specifications will have greater 3 dB bandwidth and closed-loop gain. This way you can repeat for other combinations of resistors and voltage values under standard configurations and high-gain configurations. Please subscribe to LabsLand and perform all different combinations and understand the non-inverting operational amplifier concepts thoroughly.